Now we're going to look at binomial expansion. So here I have a binomial, a bracket with two terms in it, and I'm looking to expand it. So a plus b all to the power of 5 would be a plus b times a plus b times a plus b times a plus b times a plus b. Now we should understand that we could do this longhand, but we want a shorter way of doing this. And we should also be able to use intuition to know what some of these terms would be. So for instance, my first term would be multiplying a by a by a by a by a, so I know that this should start a to the power of 5. Now the next term, I could do a times a times a times a times b, so I could have an a to the power of 4 b. But that's not the only way I could get that. I could also do a times a times a times b times a. Or I could do a times b times a times a times a. I've got a lot of different choices as to how I can create an a to the power of 4, b to the power of 1. So in a previous video we talked about how we could count these choices. Now, because multiplication is a commutative operation, order doesn't matter, and because order doesn't matter, I know that the way I'm going to do this is to say, well, I've got 5 to choose from, and I'm looking just to pick one lot of b. So this is 5 choose 1. In the same way that if I was looking to pick a 3 times and b twice, well, a 3 times and b twice, how many different ways can I do that? I've got 5 choose 2 ways of picking 2 b's from a set of 5. Then continuing, I would have 5 choose 3, lots of a to the power of 2, b to the power of 3, plus 5 choose 4, a to the power of 1, b to the power of 4, and finally 5 choose 5, lots of, well, continuing the pattern, a to the power of 0, b to the power of 5, which I might actually choose to do for the first one just for completeness. Here I haven't picked any b's at all, so this would be 5 choose 0. Now these are things that we can work out on a calculator, or you can work out by using a formula, which we'll come to later in the video. But the coefficients here would be 1, 5, then 10, 10, 5, whoops, and 1. And that would be my answer. I would have a to the power of 5 plus 5 lots of a to the power of 4b plus 10 lots of a cubed b squared plus 10 lots of a squared b cubed, 5 lots of a b to the power of 4, and then finally b to the power of 5. What we want to look at now is taking this to a general expression for n terms. Now I can't obviously write out n brackets because I don't know how large n is, so I need a slightly different way of writing this down. It follows the exact same pattern. I know that first of all I'd be multiplying a by itself n times. I know that in the next one I would be multiplying a by itself n minus 1 times, and then b 1. In the next one I would have a to the power of n minus 2, b to the power of 2, and so on and so on and so on. What I need to sort out is my coefficients, so here I would have n choose 1 different ways of doing this. Here I would have n choose 2 different ways of doing this, and so on and so on and so on. Again, for completeness, I'm going to write in here b to the power of 0 and n choose 0 in here. Now what we should notice is that this is very formulaic. The power of a is always decreasing. It begins at n, which I get from my exponent, and it decreases and decreases as we go. The power of b is increasing. It starts at 0, moves to 1, then 2, then 3, all the way up to n. N is always the top version of my choose, and the bottom can come out from either the exponent for b or the exponent for a. Again, because this is symmetric, n choose 0 is the same as n choose n, in the same way that n choose 1 is the same as n choose n minus 1, and so on. A final nice little check is that if I add these two exponents together, I should always end up at n. n minus 1 plus 1 gives me n. n minus 2 plus 2 gives me n. So just to tidy that up, that's what I have nicely written down here. Again, we've got this choose notation, so n choose r is simply n factorial over r factorial and minus r factorial, remembering that n factorial is simply n times n minus 1 times n minus 2 times, and so on and so on and so on. I would draw your attention to this term, which is a generic term from this expansion. N choose r, a to the power of n minus r, b to the power of r. Again, these exponents will always add up to give us n, and we've just got n choose the second exponent. So let's go off and see how we can apply that. So we're going to use the binomial theorem to expand this bracket. My preferred method of doing this is to start with the indices, then add on the choosing coefficients, and then to calculate. So what I mean by that is to say that I'm going to start with 2 to the power of 4 minus 3x to the power of 0, 2 to the power of 3 minus 3x to the power of 1, 2 to the power of 2 minus 3x to the power of 2, 2 to the power of 1 minus 3x to the power of 3, and 2 to the power of 0 minus 3x to the power of 4. Now I need to include my choosing coefficients, so this first one would be 4 choose 0, next one would be 4 choose 1, next one would be 4 choose 2, 4 choose 3, and 4 choose 4. Notice also that I've used brackets here for my second term, the negative term, and I'm doing that specifically because I want to track that negative. I want to make sure it doesn't get missed. Now, I'm going to calculate these piece by piece. So to start with, I'm going to calculate my choosing terms. We can do this on a calculator if we would wish, or we can just work them out from Pascal's triangle. So in this case, we would have 1, then 4, then 6, then 4, then 1. 2 to the power of 4 is 16, 2 to the power of 3 is 8, 2 to the power of 2 is 4, 2 to the power of 1 is 2, and 2 to the power of 0 is 1. Minus 3x to the power of 0 is 1, minus 3x to the power of 1 is minus 3x. I'm keeping that in a bracket because it happens to be negative. Minus 3x squared gives me 9x squared, being careful to put the square right the way through both terms. Again, it's another good reason for having brackets in here. Minus 3x cubed gives me minus 27x cubed, and finally minus 3x to the power of 4 gives me 81x to the power of 4. Now in my last step, I'm just going to make sure that I've got these final bits multiplied together. Oh dear, what's going on with the screen? So in this case I've got 16 plus 32 times 3, which is 96. That's negative, so that's minus 96. 6 times 4 is 24. 24 times 9 is 216 x squared. That's 8 times 27. 8 times 27 is, again, 216. Again, being careful with the negative, so that's minus 216 x cubed plus 81x to the power of 4. Now I've got a little tiny weeny bit of tidying up that I'm going to do now, which is just to put that in as minus 96. Oh dear me, I've dropped an x there. Plus 216x squared minus 216x cubed plus 81x to the power of 4. Now, as a good general check, if you've got a negative involved here, the signs will always flip. So you should always see on your bottom line a flipping of signs, negative, positive, negative, positive, negative, positive. If everything here is positive, obviously everything in our answer is going to work out to be positive. Right, finally, let's have a look at this, where we don't need to work out the whole expansion, we're just using the binomial theorem to find the coefficient of x cubed in this expansion. Well, where is x cubed going to come from? It's going to come from doing minus x over 2 cubed. Now, as we've talked about the exponents having to add to make 10, then the other term is going to have to be raised to the power of 7, because 7 plus 3 will make 10. And what do I need to put on front of it? My choosing coefficient, which is going to be 10 choose 3 in this case. Again, working that out piece by piece, 10 choose 3 is 120. 1 to the power of 7 is 1. And then in here, I'm going to have minus x cubed over 8. Again, being careful here that I take that negative into account. Tidying that up, I'm then going to have minus 120 over 8x cubed, or minus 15x cubed. Now the question asks for the coefficient of x cubed, so my answer here would simply be negative 15. And that's the lot.